Well, hello, my fellow students. Um, so this is Mrs. Bigelow, and this is my first attempt at teaching using PowerPoint and being able to write on a tablet and all this kind of fun stuff. So again, bear with me. I think it's going to be fun when I finally get the hang of it. So our lesson today is Goal 2 of Chapter 5, Section 2. And the title of the lesson is Angle Bisectors of Triangles. So in the last couple days we've been talking about segment bisectors and then angle bisectors, and then yesterday we talked about perpendicular bisectors of a triangle. So we bisected the sides with perpendicular bisectors, and we had a theorem that said where they meet in the middle, where their point of intersection, which we called the point of concurrency, is equidistant to the vertices of the triangle. Today we're going to bisect the angles, and so I'm going to go to the next screen, see how this works. So I'm going to give you a couple definitions. We are on page 274. This is only going to be successful if you follow along in the book. I'm going to refer to it a lot. So again, it's using angle bisectors of triangles. We're on page 274. And you guys are all familiar with the definition of an angle bisector. So we just throw in the angle bisector of a triangle, and it's just all three of the angles of the triangle are bisected. The incenter is where the three bisectors intersect. The point of concurrency is their incenter. So yesterday the point of concurrency of the perpendicular bisectors, which bisected the sides, was called the circumcenter. Today the point of concurrency of the angle bisectors is called the incenter. I'm going to go ahead and flip over to the next screen. That gives us our one theorem in this section. It's called the concurrency of angle bisectors of a triangle theorem. It's again on page 274. And what it says is that the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So this is when I start drawing. Alright, so let's say we have a triangle. Okay, and we are talking about angle bisectors. Change the color. Oh, what color do you guys want? Ah, purple. Yeah, purple, black, and white, right? Okay, go Lions. Alright, so I'm going to take... that didn't come out purple, did it? You know, I think I'm going to try and erase on here. Oh, let's start over. It's kind of fun. Okay. So... it's weird. Let me erase it again. You guys are all going to be having fun with this, huh? Probably going to be going, hey, would you just get on with the lesson, Mrs. Bigelow? Alright, so if I draw a triangle, and I draw its angle bisectors. There we go. Hopefully that, oh no, we wanted to do purple, huh? Okay, so if I bisect this, yeah, there we go. So if I bisect this angle, and I bisect this angle, and I bisect this angle. So what we're saying is, this angle is congruent to this angle, this one is to this one, and this one is to this one, right? Because those are angle bisectors. So where they meet, where they intersect here, is called R. This is the point of concurrency. Of the angle bisectors. But we have an easier term for that, and it's just called the incenter. All right? So again, angle bisectors, they meet in the middle of the triangle. And good question for you, do they always meet in the middle? Yesterday, when we had our perpendicular bisectors, they could actually meet outside, huh? So a good thought for you guys to think about. So we have our angle bisectors, and they meet right here. We call that point of concurrency, we call it the incenter. Okay? All right, so let's go to the next slide. With regard to the theorem, if we have a triangle, and let's use, it's kind of Christmas time, right? We'll use green. We bisect those angles. I think I'm going to have fun with this. Mr. Bigelow's in the background laughing. Okay, so here's our incenter, right? So we know this angle is congruent to this angle. This angle is congruent to this angle. And these two angles down here are congruent. Why? I'll let you answer that. Okay, so what the theorem says, the concurrency of angle bisectors of a triangle says, is if you have the three angle bisectors, they are going to intersect at a point that is equidistant from the sides. I'm going to go back and I'm going to refer to what equidistant means. If I draw a line, I'm trying to get really creative with the colors here, but I'm ending up back to black. If I bring a line straight down from that point, it has to make a 90-degree angle with that side. And if I do that to all three sides, this segment is congruent to this segment, is congruent to this segment. Okay, so if we give some letters on here, and we have A, B, C, let's call the middle P, D, E, and F. Basically what I'm saying here, again, is the angle bisectors meet at a point that is equidistant from the sides. That means that the length of line segment DP is equal to the line segment of EP, which is equal to the line segment of FP. Pretty cool, huh? Stop talking, Brian. I just had to do that. All right, so next screen, let me just give you one example. Example 1. So say, and basically this is going to be your example in the book, example 2 in the book. So we have this big triangle. Right? We'll bring those angle bisectors in to purple. Okay. We have that angle congruent to that angle, that to that, and that one to that one. Okay. So I'm giving you this information. I take a line segment and take it over from that incenter over to the three lines. What I'm gonna give you a little bit of information here. Here's M, S, and P, R, N, and Q. I'm going to give you a little bit of information here. MQ is 15. And I'm going to call this point in the middle L. And I'm going to tell you that ML is equal to 17. I'm going to ask you 2 questions. I'm first going to ask you, what segments are congruent? I'll give you a minute there. The answer to that question would be this segment, and this segment. So QL is equal to, I'm going to rephrase that, the distance, the length of line segment QL is equal to the length of line segment SL, which is equal to the length of line segment RL. Right? So now I'm going to ask you another question. What is the length of LQ and LR? And to answer that question, I'm going to have you look at the triangle LMQ. From here, I want to go green on that one. Okay, LMQ. Okay, it's a right triangle, right? So let me draw it again out to the side. So take an arrow, draw it out to the side, tip it up, and redraw it like that. So you'll see that this leg is 15. And the hypotenuse is 17. So how am I going to figure out how long QL is? Yes, you are correct. We are going to use the Pythagorean theorem. I'm going to let QL be x. And I'm going to say that the length of QM squared plus the length of QL squared plus, equals the length of ML squared. So we know QM squared is 15, squared is 225, plus, we don't know what QL is, but we called that x, so that's going to be x squared equals 17 squared is 289. Okay, take the rest of this math over here. So we have 225 plus x squared equals 289. Subtract 225 from both sides of the equation. X squared equals 64. And yes, x equals 8. So that means LQ right here is 8, right? And so is SL. And so is RL. Okay? Alright, so I hope this went well. I'm going to go ahead and go to the next screen and write down your homework. And play well, play the glory of God, and win those games. Alright, boys and girls? Have a great day. This is Ms. Bigelow. Signing out. Okay. You know, I'm just going to write the homework up here. It is homework. Pause for a second while I find that. I believe it's 40. It's a short homework. I think you guys will be pleased with that. So it's homework 43 pages, 275, 278, numbers 15, 16, and 22, and 33 through 39 odd. Have a great day, guys. Bye.